Welcome to the deep dive.
Yeah.
Okay, imagine you're trying to build probably the most complex thing humanity has ever created, a modern processor chip.
Right, with billions and billions of transistors.
Exactly. And the real problem isn't even building it, it's just checking if the thing works. How do you simulate and verify something so vast when the number of possible states is just astronomical?
That is the crisis we're diving into today. It's something we call the memory wall.
The memory wall.
Yeah. Your traditional data structures, all the things you rely on, like, hash tables or complex decision diagrams,
The classics.
they demand memory that scales linearly, or sometimes even worse, with the chip's complexity. So you run your simulations, you generate all this verification data, and then boom, your system just grinds to a halt.
Because you've run out of memory.
Completely. The memory you need to track everything just exceeds what's physically possible. It leads directly to, well, computational paralysis.
So the bottleneck isn't processing power anymore. It's just the sheer volume of data we have to store and sort through in real time.
Absolutely. And you have to think of it as streaming data. During a simulation, you can't just pause to save every single transaction. You have to process it as it happens.
Which forces a strategic decision.
It does. You have to trade absolute 100% certainty for massive gains in efficiency.
And this is where we get into the world of probabilistic data structures, or PDS.
Exactly.
We're talking about embracing a controlled, mathematically bounded degree of error. For what? For sublinear memory use and constant time operations. This isn't just a hack, it's a calculated engineering move.
That's the key takeaway. It's a trade-off that is, it's essential for survival in modern hardware design.
So today we're unpacking the three heavy hitters that make this possible. First, we have Bloom filters. They're all about testing set membership. Then Countmin sketches, which are essential for high-speed frequency estimation.
And finally, hyperlog log. That's the state-of-the-art for scalable cardinality counting.
Yeah.
The famous count distinct problem.
Okay, let's unpack this. We have to start with Bloom filters, the elegant solution to what's called the state space explosion problem.
Right.
So what's the core mechanism here? How do we check if something's in a set without actually storing the whole set?
The mechanics are deceptively simple. You take a big bit vector, just a long string of zeros, and you use multiple independent hash functions, let's say k of them.
Okay.
When you want to insert an element, say a specific chip state you just visited, you compute those k hashes. Each hash points to a position in the vector, and you just flip that bit to a 1.
And the query is where the probabilistic part kicks in.
That's it. To check if you've seen that state before, you hash it again with the same functions. You look at all the corresponding bits.
If any of them is a 0,
Then it is definitively not in the set. Impossible.
but if they're all 1s,
Then it's probably in the set.
that asymmetry is the critical part, isn't it? You never get a false negative.
Never. The only error is a controlled false positive rate. You might occasionally think you've seen a state when you actually haven't because of a collision.
But wait, hold on. If we're using this for formal verification, like with bit state hashing, and we're accepting these collisions to save memory, doesn't that make the whole verification technically unsound? Couldn't you miss a critical bug?
That is the essential risk calculation. And yes, you're right, it is technically unsound.
So why do it?
Because here's the crucial insight. This so-called unsound verification is often superior to a complete deterministic search.
How can that be?
Because the deterministic approach runs out of memory so fast that it might only cover, say, 1% of the total state space. It's perfect, but for a tiny little corner of the problem.
Ah, I see.
By accepting a tiny mathematically bounded chance of a collision and using just 2 or 3 strong hash functions reduces that chance exponentially, you cover vastly more ground. You find more bugs faster.
So you're trading perfection for massive coverage gains. And this isn't just a software trick. These are actually designed into the chips themselves, right?
Oh, they are baked right into the silicon. A great example is the load store queue, or LSQ, in a high-performance microprocessor.
What's that do?
It has to handle incredibly complex memory operations, and running traditional, expensive associative searches to check for dependencies is extremely power-hungry.
So they use a Bloom filter.
Exactly. They integrate them as search filters to quickly rule out memory operations that are unlikely to conflict.
And what's the real-world benefit of doing that in hardware?
It's huge. By using these optimized, what are called encoded Bloom filters, designers get significant power efficiency gains with a really negligible performance hit. We're talking about an average of around 1%.
Wow.
It just shows how precise that trade-off can be when you implement it correctly.
Okay, so if Bloom filters track presence, Let's move on to the second structure. Count min sketches, or CMS. This is for frequency. It answers, how often has this thing happened?
Precisely. And CMS is essential for identifying what we call heavy hitters in massive streams of data. It's crucial for any kind of dynamic optimization.
And the structure is different, right?
It is. It's a two-dimensional array of counters. Think of it like a grid, maybe D rows by W columns. Each row uses its own independent hash function.
So when a new item comes in, you update it across all the rows.
All D rows, correct. You increment the corresponding counter in every single row.
Okay, so then to query it, to estimate the count, you check all the rows again.
You do. And you always take the minimum value you find across those D counters.
The minimum. That's interesting. Why not an average? That seems more intuitive.
It does, but it's because of the error profile. A hash collision, where two different items land in the same counter, can only ever cause the count to be overestimated.
Ah, of course. It adds counts together.
Exactly. The sketch never, ever underestimates the true frequency. So taking the minimum value across all those independent rows gives you the tightest, most accurate bound on the real frequency.
That's a critical distinction. It never underestimates. Now, you mentioned it's biased because it only overestimates. That sounds like it could be a problem for identifying the low-frequency items, the mice in the whole elephants and mice problem.
It is a problem. In EDA data, the data is often incredibly skewed. You'll have a few things that happen trillions of times, and most things happen only once.
And those big elephants would just pollute all the counters.
They do. So there's a key refinement called the conservative update, or CMSCU.
Right.
Instead of just blindly incrementing all G counters, the update only increments the counter, or counters, that currently hold the minimum value. This dramatically reduces the overestimation from collisions and gives you a much cleaner signal for those rare items.
Yeah, it's really elegant. Let's connect this to a hardware case study. NeoProf, the CXL memory profiler.
A great one.
So in these massive systems with CXL expanded memory, you need to know which memory pages are hot so you can migrate them. But doing that with normal counters across terabytes of memory is just impossible.
Impossible. NeoProf uses a hardware-based pipeline CMS array to track those page access frequencies using a bounded amount of memory. But here's the really clever part. They avoid the bandwidth bottleneck of reading the whole sketch. Instead, a dedicated histogram unit reads just one row of the sketch. That single probabilistic sample gives them enough data to estimate the entire frequency distribution.
So they're using a guess to avoid reading tons of data. And that lets the host CPU set a dynamic hotness threshold.
Precisely. And to get this running at max speed on, say, an FPGA, designers use really aggressive optimization techniques to achieve what's called an initiation interval, or 2 of 1.
What does indecigate of 1 actually mean for our listener?
It means you are maximizing the pipeline. You're scheduling everything so perfectly that the hardware can accept and process a new data point every single clock cycle. You're processing data at the clock speed of the chip.
Okay, let's move to our final structure, hyperlog-log, or HLL. If CMS finds the heavy hitters, HLL solves the problem of counting how many unique things have happened, the count distinct problem.
And HLL is the undisputed champion of space efficiency. I mean, it's not even close.
Give me the numbers.
We're talking about estimating cardinalities of over 1 billion unique items with a standard error of about 2%, using only about 1.5 kilobytes of memory.
Wait, what? 1.5 kilobytes.
That compression ratio is, frankly, mind-boggling.
How does that even work? How can counting leading zeros in a hash value tell you how many unique items you have?
It's all rooted in probability. Think of it like this. If you flip a coin, the chance of getting a run of, say, 4 heads in a row is pretty rare, 1 in 16.
Okay.
The chance of getting 10 heads in a row is astronomically rare.
Right, I see. So the longer the run of heads, or in this case leading zeros, the rarer that event is, which means the sample set must have been there to produce it.
Exactly. When HLL hashes a massive set of items, it's like running trillions of coin flips. If it sees an item whose hash starts with a maximum of, say, 10 leading zeros, it can probabilistically infer that the set must be very large, because it took many, many tries to hit that rare 1 in 1,000 outcome.
But just relying on one single observation would be super volatile. How does it smooth out that randomness?
Through stochastic averaging, HLL splits the data into many smaller independent buckets, let's say 124 of them, and for each bucket, it cracks the longest run of leading zeros it has seen.
And then it averages them.
Not quite. It calculates the harmonic mean of their values. The harmonic mean is much less sensitive to extreme outliers than a regular arithmetic mean, which dramatically increases the reliability of the final estimate.
And I know Google's HLO plus algorithm took this even further. It fixed some of the edge cases, right?
It did. For very small counts where the registers are mostly empty, HLO++ is smart. It switches to a different method called linear counting to give near exact answers.
So it adapts.
It adapts. It also uses a sparse representation to save even more memory when counts are low, only switching to the denser format when it's necessary.
The absolute killer feature for the EDA world, for coverage-driven verification, has to be HLL's mergeability.
Oh, absolutely crucial. You can take two HLL sketches and combine them instantly just by taking the element-wise maximum of their registers.
And that's transformative for distributed verification.
It is. You could have thousands of simulation farms running, all generating coverage data, instead of sending petabytes of raw logs back to a central server.
You just send these tiny 1.5 kilobyte HLL sketches.
And the verification manager merges them instantly to get a global, accurate view of the total coverage. It also lets them monitor coverage growth in real time if that HLL estimated number starts to plateau.
It's a clear, data-driven signal that your current tests aren't hitting anything new.
Exactly. It tells you to refine your stimulus right now without waiting hours for a full data aggregation run.
Okay, so let's synthesize this. We have the individual structures. How does PDS transform the bigger picture of EDA and hardware resilience?
Well, these structures are becoming foundational everywhere. Take hardware security. Bloom filters are used to monitor internal signals, but they're not looking for common errors. They're looking for extreme rarity. If a complex state is triggered that was never, ever seen during billions of simulation cycles, that rare event could be the trigger for a malicious hardware Trojan that's been lying dormant.
And the fact that these are all inherently error tolerant, that plays into the trend of approximate computing.
That's the resilience angle. The output of a sketch is already fuzzy, so if a single bit flips because of a soft error, the system doesn't crash.
The error rate just goes up by a tiny acceptable fraction.
Right. And that means you can store these sketches in approximate memories, like SRAM or DRAM running at lower voltages, and get power savings of up to 60% with almost no impact on the final accuracy.
So we're saving memory, increasing energy efficiency, and making the system more resilient, all by embracing this controlled imperfection. What are the roadblocks then? What's stopping this from being everywhere?
The main challenge is dynamic sizing. Standard PDS are fixed size. If your simulation is unpredictable, the sketch can saturate and your results get inaccurate. There are scalable versions, but they add complexity.
And resources.
And resources, absolutely. On an FPGA, a high accuracy sketch can eat up 60, 70, even 80% of your scarce on-chip RAM. So designers are in this constant agonizing fight, balancing accuracy versus what's actually available.
Finally, let's look at the cutting edge, generative EDA. Using LLMs to write hardware code, how does PDS fit into that future?
It's critical. To train an effective hardware LLM, you need to deduplicate massive code bases to make sure the model is learning diverse patterns. HLL is perfect for that. And after the LLM generates a chip, Bloom filters are being used for real-time assertion monitoring, basically checking the LLM's work against known good patterns to flag anomalies instantly.
So after all of this,
Yeah.
what does this whole deep dive really mean for the philosophy of engineering?
It means we successfully found a way around the memory wall. The strategic choice to trade absolute certainty for confidence has unlocked the next era of complexity.
Bloom filters beat the state space explosion,
CMS gave us high-speed telemetry for systems like NeoProf.
and Hyperlog log delivered scalable global coverage tracking.
Right.
This philosophical pivot from proving with certainty to estimating with confidence, that feels like the most profound takeaway.
I agree completely. It validates the idea that at a certain scale, complexity demands approximation. We're in an era where trusting the mathematical bounds of probability is essential for progress. We have to ensure that the limits of our memory do not become the limits of our imagination.
And that leads us to our final thought for you. If engineers designing the most mission-critical parts of a processor can embrace this probabilistic approach for massive games, what deterministic constraint in your own field, whether it's finance, logistics, or data analysis, could be safely approximated today to achieve a breakthrough? What certainty are you holding on to that is now limiting your growth? Something to think about until our next deep dive.